So here I would like to prove the Maclaurin's formula. The Maclaurin's series. It is a formula that is used to express certain functions as an infinite sum of terms in the form of ax to the power of n. So we are saying if we are given f of x is equal to, let me just write it down here, f of x is equal to a naught plus a1x plus a2x squared plus a3x to the power of 3. Then we keep on going, numbers and ending like this. This can be summed up by a technique created by Maclaurin, which is called the Maclaurin's formula. The understanding behind this is the coefficient of a naught can be found by setting x is equal to 0. So we are saying the coefficient of a naught can be found by setting x is equal to 0. So basically we are saying this polynomial is about the origin as its center. So when we set x is equal to 0, that is, we are saying f of 0, and if you place 0 where there is x, everything else becomes 0. We are just left with a naught equal to f of 0. If we differentiate f of x successively, if we differentiate f of x successively, you can do it maybe 3 times. It gives us the first derivative is f prime of x. So if we differentiate this part, this is a constant, it becomes 0. But this is x, so it becomes a1. And this becomes 2, a2x, and this becomes 3, a3x squared. We can keep going, and this becomes r, arx, r minus 1, like that. If we do it again for the second time, I'm just going to do it for 3 times. F double prime of x gives us, so this is now a constant, it becomes 0, so we are left with 2a2 plus 3 times 2 a3x. Can keep on going, plus r minus 1 arx r minus 2. I'll just do it for the 3rd time. This becomes 0. Then we are left with 3 times 2 a3 plus, we keep on going, this becomes r minus 1 r minus 2 ar, like that. Likewise, so there is a repetition, a shape, a formula, a pattern that is being generated. So if you are well much aware of the numbers that are being created here, you can see that if you understand this term, which we call the factorial, n factorial stands for n times n minus 1 times n minus 2. You can keep going like that. So for easier understanding, if I have a number like 4 factorial, I can write it as 4 times 3 times 2 times 1. If I have a number like 3 factorial, I can write it as 3 times 2 times 1. So 2 factorial, I can write it as 2 times 1. Just like that. I'm saying this because you can see from the numbers that I've generated that there is a factorial pattern. So you can see this is a factorial pattern, 3 times 2. You can write it as 3 factorial. R minus 1, R minus 2, we can write it as R factorial. So that's basically what happens. So if I now continue, as I've done here, set out x is equal to 0 and evaluate each term. So if we evaluate each term at x is equal to 0, means we're going to have f prime of 0 here being equal to a1, suggesting that a1 is equal to f prime of 0. Then f double prime of 0 is equal to 2a2. So it's 2a2, suggesting that a2 is equal to f double prime of 0 over 2. But my 2, I want to write it as 2 factorial. Then f triple prime of 0 becomes 3 factorial a3. Rather, let me write it in the original as it is 3 brackets 2, then a3, which suggests that a3 is actually equal to f triple prime factorial of 0 over 3 factorial. So the last one will be f of r. So f of r at 0 is actually going to be equal to what? R factorial AR, which suggests that AR is equal to f of r at 0, R factorial. So as you can see with this, we can move in now to substitute in our polynomial where there is a naught, we will leave as a naught. Where there is a1, we will write f prime of 0, then x. Where there is a2, we will replace a2 with f double prime of 0 over 2 factorial x squared. Where there is a3, we will replace with f triple prime of 0 over 3 factorial of x cubed. So we can keep on, let me create some space here, going. So we've already written this. We can keep on going, plus dot dot dot, plus f of r, because we are here where there's ar x power of r. So this will also be written as f of r of naught over r factorial, then x to the power of r. It keeps on going. So this is the Maclaurin's series. It can be used to write so many functions in an infinite form. However, the function can only be written, can only be written in that given form only if the series is going to converge. And again, only if the derivatives can exist for an infinite number of times. So it doesn't work all the time, but it gives us a way of solving those infinitely power series.